So there are 9 hydrogens over here, 9, and then you have 2, so it's going to be 9 to 2. Okay, for question number 8. And then for the number 9, what is the integration for each set of protons in the proton NMR spectrum? What is the integration? Now, how do we look at the integration? It is the number of protons. Okay, so for A, how many hydrogens are on A? There are 3 hydrogens. So on A there are 3 hydrogens. So that's the integration. And then the B has 2 hydrogens. And then the C has 2 hydrogens. And D has 2 hydrogens. And E has 3 hydrogens. Okay. So that is going to be C. A 3 hydrogen, B 2 hydrogen, C 2 hydrogen, D 2 hydrogen, and E 3 hydrogens. That's EC. Integration is the number of protons on each carbon. What splitting pattern is observed in the proton NMR spectrum of the indicated hydrogen? Now remember, splitting happens due to the hydrogens on the adjacent carbon. Now, if this is your benzene ring, and then you have oxygen, and then you have 2 hydrogens over here, and then you have 3 hydrogens at the very end. Now, if you look at this molecule, how many different environments we gonna have? We have different environments. Like this is a different environment and this is a different environment, and then you have hydrogens on the benzene. This might this might separate the hydrogens in the benzene ring to have it in different environments because it is connected to a electron withdrawing oxygen atom, right? So let's forget about the hydrogens on the benzene ring, but let's look at hydrogens on your ethyl group. So the carbon 1, carbon 2. If you look at carbon 1 and 2, you would see 2 different signals on the NMR spectrum. And their ratios are going to be 2 to 3 because in the carbon 1 there is 2 hydrogens. Carbon 2 has 3 hydrogens. Okay. Ratio is going to be 2 hydrogen to 3 hydrogens. And if this is your TMS, which is the reference point, and I put 2 hydrogen more closer to the downfield, and more upfield would be 3 hydrogens because it's closer to the carbon, whereas this number 1 carbon is closer to the oxygen. Okay, it would be more D-shield. So this is how the splitting happens. If you consider the carbon 2, there are 3 hydrogens. So those 3 hydrogens are going to split due to the hydrogens on the neighboring carbon. So the neighboring carbon is carbon 1. And we normally consider 3 bond coupling, not beyond 3 bonds. So 3 bond means if you consider this hydrogen, how many bonds we are looking at? 1, 2, 3. And then 1, 2, 3. So 3 bonds. The 2 hydrogens on the carbon 2 are 3 bonds away from the hydrogens on the carbon 2. So the 3 hydrogens here is going to split due to the 2 hydrogen on carbon 1. And when it splits according to the n plus 1 rule. Now n is the number of hydrogens in the neighboring carbon. If you consider number 2 carbon, your neighboring carbon is going to be number 1. So the neighboring carbon has 2 hydrogens. So 2 plus 1. So carbon 2 will split to a triplet due to the 2 hydrogens on carbon 1. So if you look at the splitting pattern, So so this is going to be number 2 carbon, number 1 carbon. So the number 2 carbon will be a triplet due to the 2 hydrogens on carbon 1. And similarly, carbon 1 is going to split due to the 3 hydrogens on carbon 2. So for the carbon 2, there are 3 hydrogens. On carbon 2, there are 3 hydrogens. So the carbon 1 hydrogens will split due to the n plus 1 rule. So the n going to be 3, so 3 plus 1, 4. So carbon 1 hydrogens will split to a quartet due to the 3 hydrogens on carbon 2. So it would become quartet 1 to 3 to 3 to 1, like that. So this is carbon 2, this is carbon 1. Okay, 1 and 2. That's how you observe the splitting. I hope you got it. Okay, and then number 11. So look at the answer for number 10 would be, it's a triplet, right? Methyl group would be a triplet due to the 2 hydrogens on the neighboring carbon. You see here this carbon has 2 hydrogens, so n plus 1. So n is 2 plus 1, it's a triplet. Okay. And number 11, how many triplets would you expect to see in the proton NMR of the compound below? How many triplets? Okay, so this is a molecule that is not showing you hydrogens, but we do have hydrogens on these positions. Okay. How many triplets do you see? Triplet means the neighboring carbon carrying 2 hydrogens. So if you consider these 2 hydrogens, okay, that can be split due to the neighboring carbon carrying 2 hydrogens. Same thing. Okay, so these 2 hydrogens, if they are in different chemical environment. But let's see if they are in different chemical environment or they are in the same chemical environment. Now look at the molecule. So in this molecule, you can see there is a methoxide group on this end, OCH3. It's the same group, OCH3 groups on the other end. Okay, and then on the middle carbon, you have 2 methyl groups right there. And then you have 2 carbons with carrying 2 hydrogens on either side, making all the CH2 hydrogens chemically equivalent. If they are chemically equivalent, they are not in a different environment. They are in a one environment. But you have to see what are the similar environment out of these 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Okay, so due to the symmetry of the molecule, the green circle hydrogens are going to be chemically equivalent to these 2 hydrogens. They are chemically equivalent. Those 4 hydrogens, they are going to be chemically equivalent. And let's look at the other hydrogens. Red, let's use red. So these 2 hydrogens and these 2 hydrogens, they are going to be chemically equivalent, right? But the green hydrogens and the red hydrogens are not chemically equivalent because the green hydrogens are closer to a methoxide group and then the carbon with CH2 and another group, right? So due to that, the green hydrogens would be in one environment, red hydrogens would be in one environment. Okay, and then they are next to 2 hydrogens, so that will create a 1 triplet for the red hydrogens and 1 triplet for the green hydrogens. So we're going to have 2 triplets total because of the symmetry of the molecule, and some of the hydrogens happen to be in the same chemical environment. So the answer is going to be 2 triplets. Okay. And then the number 11, in the proton NMR, indicated methyl group will show up as a what? Again, we are looking at 3-bond coupling. Okay. So if you expand this molecule and see what are the atoms that are not showing, so there is a hydrogen over here, and then indicated carbon has 2 hydrogens. According to the 3-bond coupling, excuse me, so the 2 hydrogens that you have on the on this carbon will split due to the hydrogen that you have on that alcohol carbon, and that is a 3-bond coupling. So as a result, indicated hydrogens would show up as a doublet. Number of hydrogen is here in plus 1, 1 plus 1, so that's going to be a doublet. Okay, and it will not split due to the hydrogen because it would make it 1, 2, 3, 4 4-bond coupling. That would not happen. Okay, so the next one, which of the following gives proton NMR spectrum with the following signals? You have a triplet at 1.21, triplet at 1.21, 3 hydrogen singlet at 2.30, a quartet at 2.60 ppm, and then singlet at 7.04 ppm. 4 hydrogens. Okay, so now we are given some information. Now this is like putting a puzzle pieces together. We use the chemical shift values and also the splitting pattern to figure out what would be the correct structure with the given chemical shift and the splitting data. Okay. Now this one says there is a triplet at 1.21 ppm. How do you get a triplet? You get a triplet if you have a CH2 group next to the carbon of interest. Okay, so triplet would result due to a CH2 group in a molecule. And then we are also given there is a 3 hydrogen quartet. Okay, 3 hydrogen quartet at okay, so let me see, triplet 1.21 ppm, 3 hydrogen. Okay, so there is a 3 hydrogen, that's a triplet. So this is CH3 group. There should be a 3 hydrogen next to that. So it says triplet at 1.21 ppm, that's a 3 hydrogen. So 3 hydrogen triplet would be, you should have a group in your molecule like CH2, CH3. Okay, and then here you also have a singlet at 2.30 ppm. So this is another piece. Singlet at 2.30 ppm, 3 hydrogens. The singlet means you should have a methyl group and then you have something that would not contain any hydrogens on it. Okay, that's the second piece of information. And then you have a quartet at 2.6 ppm, a quartet, 2 hydrogens quartet. So the 2 hydrogens quartet would be these 2 hydrogens. This would be a quartet due to the neighboring 3 hydrogens. So this is at 2.60 and this methyl group at 1.21. So this is the hydrogen that talks about 1.21 and then the CH2 is at 2.60. And then you have a methyl group, a singlet 2.30. So 2.30. 30 chemical shift, you have that singlet. And then you also have a singlet at 7.4 ppm. 7.04 ppm, there is a 4 hydrogens. Meaning around 7 ppm we get benzene hydrogens. So you can know that it's going to be a benzene ring. There are 4 hydrogens. They all are at 7 ppm. There's 4 hydrogens. Now we know, excuse me, our molecule, we have a piece similar to this, and in our molecule we have a piece similar to this. Okay, excuse me. So we can put our CH2 CH3 group on one end, and then the methyl group has to be on the other end. Okay, so 4 hydrogens are going to be these 4 hydrogens. Okay, so that tells us the structure of the molecule with the given data is going to be B. Okay, so why it is not 1? Because in 1 we have 3 hydrogens triplet, 2 hydrogens sextet, and another 2 hydrogen a triplet. We don't have that information. So number 3 we will have 6 hydrogen doublet and 1 hydrogen septet. That's not given either. And number 4, there are 3 methyl groups. Then we need to have a singlet, but we don't. 3 methyl group singlet is not given, or 9 hydrogen singlet, or like that. Okay, 3 hydrogen singlet. And number 5 is also not correct, because we're going to be having singlets for that, because the benzene carbon. So if you look at what is the meaning of singlet, so this is your benzene ring, and this is carbon, hydrogen, hydrogen, hydrogen. Remember, so this is your benzene ring. We go by 3 bond coupling. So if this is 1 bond, 2 bond, and then on this carbon over here, we need to hydrogen if it is going to give us any splitting. But in that benzene carbon, we don't have any hydrogen. If you put a hydrogen, that would make 5 bonds to that carbon. So that is another carbon is what we have. So because of that, you don't have a coupling when the methyl group or any group attached directly to the carbon other than hydrogen. So this hydrogen not there. Okay, so that's why we call it as a singlet. I hope you got it. So this is the chemical shift table. I just put it over here so you to remind where each kind of hydrogens appear. So basically methyl groups, CH3, very low chemical shift, 0.85 methyl, and methylene going to be 1.20. Okay, CH2. When you have another carbon, and then the CH, there are 3 carbons there. So that is 1.55. And then hydrogen next to a double bond, and so on. If the hydrogen is next to a group that carrying a carbonyl group, it comes around 2.1. And for the benzene hydrogens. Okay, see here, benzene hydrogens between 6.5 to 8. So that's what we saw, around 7 in our previous problem. Okay, and then the aldehyde hydrogens, very de-shielded, 9 to 10. Carboxylic acid, very de-shielded, 10 to 12, because of the electronegativity of the oxygen as well as the resonance stabilization over here. Okay. Okay, number 14. Which of the following compounds has a triplet, 3 hydrogen at 1.1 ppm, a sextet 2 hydrogen 1.8 ppm, 1.8, a triplet 2 hydrogen 2.3 ppm, and a singlet 3 hydrogen 3.8 ppm in the proton NMR spectrum. So the pattern is 3 hydrogens. Okay, now look at A. So all these molecules, you have hydrogens like that. So these 6 hydrogens are going to be chemically equivalent because they are in the same environment. So if A is the correct answer, we should have a 6 hydrogen going to be a doublet due to the neighboring carbon hydrogen. 6 hydrogen doublet. Do we have that in our data given anywhere as a 6 hydrogen doublet? No. So because of that, A is out. Same thing for B. Do you see B? These hydrogens here, they are going to be chemically equivalent. That has 6 hydrogen, and that could couple due to the hydrogen on the neighboring carbon to a doublet. But do we see description that there is a 6 hydrogen doublet? No. So then the B is also out. Now between C, D and E, let's look at C. So C, there is 3 hydrogens here. And then you can see 2 hydrogens here. And another 2 hydrogens there. Another 3 hydrogens right there. The splitting pattern for the C, we have a singlet. So 3 hydrogens here going to be a singlet, because there is nothing on the carbon that it can split on the neighboring carbon. That's a singlet. And then what about, excuse me. So these 2 hydrogens, there would be a blue one would be a 2 hydrogen, a triplet. Okay, the blue one, 2 hydrogen, a triplet. And then what about the orange 2 hydrogen? That 2 hydrogen can be split due to the neighboring hydrogens on the left and the right. So there are 3 on here and then 2 on the blue circled hydrogen. So there are 5 hydrogens that could be split, that could would be the reason to split the 2 hydrogens. So 5 plus 1 would be a sextet. So we have the orange one is going to be 2 hydrogen sextet. Okay, so this one is a singlet, sextet. And then what about the 3 hydrogen at the very end? These 3 hydrogens, the red ones, those 3 hydrogens would be a triplet. Okay, so that would be the pattern that we're going to be observing for that molecule. And if you look at our description, there is a 3 hydrogen triplet. Yes, we do have that. A sextet 2 hydrogen. Sextet, S-E-X-T-E-T, sextet. Okay, and then a triplet 2 hydrogen. We have that also. And a singlet 3 hydrogen. Singlet 3 hydrogen. So all of those are available there. Okay, so that looks like the correct structure. But wait, so let's look at D also. But we also have to match the chemical shift values. Okay, so here 3 hydrogen singlet. The 3 hydrogen singlet, where does it appear? 3 hydrogen singlet. Singlet 3 hydrogen. it appears at 3.8 ppm. But here this 3 hydrogen singlet is closer to a carbonyl group. When it is closer to the carbonyl group, it's not going to be chemical shift 3.8. It would be 3.8 if it is closer to a electron withdrawing group like oxygen. Okay? So because of that, you can look at the other molecule, D. There are 3 hydrogens on that terminal carbon. That is directly next to electron withdrawing group oxygen and a carbonyl group. That would increase the chemical shift. So on structure D also we have 3 hydrogen singlet, but its chemical shift is 3.8, which matches with the chemical shift that it's supposed to be. Whereas in C, 3 hydrogen singlet is not directly attached to oxygen. So because of that, it looks like our structure is D. And then also here you have 2 hydrogens. That's going to be a triplet. So 2 hydrogen triplet 2.3. 2 hydrogen triplet 2.3. That makes sense. 2 hydrogen triplet. Now in the previous one, these 2 hydrogen triplet would or should appear at a more downfield if it is this structure C. Okay, so 3 hydrogens singlet 3.8, and then you also have these 2 hydrogens as a sextet, and then these 3 hydrogens as a triplet. So the correct answer is D, because it matches with the splitting pattern as well as the chemical shift data. Now why E is not the correct one? Do we have any singlet there? No, because these 3 hydrogens would be a triplet, these 2 would be a quartet, these 2 would be a quartet, and these 3 would be a triplet. So because of that, it would not be the correct structure. So the correct structure is E. So not ED, sorry, D.